2.2, applications of linear programming. This means story problems. So you need to read very carefully and really think hard about what they're asking you to find. Let's look at example 1. Andrew Crowley plans to start a new business called River Explorers, which will rent canoes and kayaks to people to travel 10 miles down the Clarion River in Cook Forest State Park. He has $45,000 to purchase new boats. He can buy the canoes for $600 each and the kayaks for $750 each. His facility can hold up to 65 boats. The canoes will rent for $25 a day and the kayaks will rent for $30 a day. How many canoes and how many kayaks should he buy to earn the most revenue if all boats can be rented each day? There's a lot of information there and a lot of numbers. So the first place I would start, I think you should start at the end and look at what they're asking. How many canoes and how many kayaks? Let's just call that X and Y. Those are your variables. How many canoes and how many kayaks? So ideally, you'd go back through and read it again, and every time they say canoes, that's going to be an X, and every time they say kayaks, that's going to be a Y. But I also want to notice that we want to find the most revenue. We want the most money. So that's how you know this is going to be a maximized problem. So we're definitely going to maximize, write that down. And you can say Z equals, or you can put R if you want to talk about revenue, but let's just say Z. We're going to maximize Z equals, and then we're going to have some constraints. So write down subject to, this is part of the setup, and those will be your constraints that we graph. Okay, I know it's maximize. I know I'm talking about canoes and kayaks, but let's go back through, and I don't want to read the whole problem again. I want to go back and find the numbers that are talking about revenue. So we want to maximize revenue. And so when you go back and look at this, they're talking about the canoes will rent for $25 a day. So canoes are X, and the kayaks will rent for $30 a day. That's a Y. That's my revenue. That's what I want to maximize. So we're going to say maximize Z equals 25X plus 30Y. The rest of the numbers should be talking about the constraints. So go back through, and what I would recommend you do is look for inequality symbols. What I mean by that is when it says he has $45,000 to purchase new boats. That means he can spend up to $45,000. He can't spend 46, he can't spend 50, he can spend 44,000, 43,000, 32,000. He can spend anything that is less than or equal 45,000 to purchase new boats. So keep going. I see a dollar sign, but also I see this dollar sign is talking about buying canoes. So canoes is going to have an X on it, and kayak's going to have a Y on it. All three of those numbers are talking about buying boats. And so we put those together into an inequality. 600X plus 750Y is less than or equal 45,000. Okay, what else do we have? The next one, his facility can hold up to 65 boats. So again, you got to think about it. They could have 65, 64, 63. That means less than or equal to 65. They can't have 70, but they can have up to 65. So I know something is going to be less than or equal to 65. It's talking about the number of boats, and they don't spell it out there for you, but it's canoes plus kayaks has to be less than or equal to 65. So we've got X plus Y is less than or equal to 65. And that's, I think that's the hard part. Now, you also want to add in an extra little statement that says X is greater than or equal 0 and Y is greater than or equal 0. These are necessary steps to prevent us from having negative numbers of canoes and kayaks. So that's the setup, and that's the hard part. That's the new material. The rest of this is the same as what we did in last time's lesson 2.1. We're going to graph these inequalities and look for the corners. So let's go to Desmos. The first one was 600x plus 750y is less than or equal 45,000. Then we had x plus y is less than or equal 65. All right. X is greater than or equal 0. Y is greater than or equal 0. Again, I think it's easiest to see if you'll change those things all to the same color. Doesn't have to be red, but I think it's easiest to see when it's all red. We're looking at this quadrilateral shape right here. Now, I'm not going to draw a whole bunch, but I'm going to draw just kind of what I need. All right, notice I don't care about this point over here, and I don't care about this point up here. I only care about the corner points of my feasible region. So I'm just going to draw a quick sketch. I'm not going to draw it. It's not going to be fancy. It's just going to be something quick to give an idea of what this thing looks like. So we've got the axis, and we had a line that came through like this, and another line that came through like this. And inside that shape was our feasible region. So color that in. We wanted the corner points. So there's one, there's one, there's one, and there's one. I know that's 0, 0. What were the rest of them? 0, 60, and 65, 0. So this is 0, 60, and this one is 65, 0. My window disappeared. And 25, 40. Okay. So remember what we did in 2.1. 2.1, we took those corners. This is called the method of corners. We took those corners and we plugged them into the objective function. This is the objective function. So we want to plug those numbers in. 25 times 0 plus 30 times 60 is going to be 1,800. And 25 times 0 plus 30 times 0 is 0. And 25 times 25 plus 30 times 40. Might need a calculator for this one. That's 1825. And 25 times 65 plus 30 times 0. Again, calculator gives me 1625. Those are my totals. Those are my z values. I've got 4 different z values. But remember, we're trying to maximize. And so if we maximize, this is the maximum number, 1825. So the answer, the maximum, and remember what we're talking about, revenue, right? We're talking about the maximum revenue is $1,825. And then normally we'd say at x equals 25 and y equals 40, but we're talking about context here. We have context for the problem, so we need to give context to our answer. So this is if we rent 25 canoes and 40 kayaks. So mainly we're doing the same thing as 2.1. We just have that extra step of set up the problem. Let's do another one, number 2. A 4-H member raises only goats and pigs. She wants to raise no more than 16 animals, including no more than 10 goats. See how you might recognize some inequality symbols there? She spends $25 to raise a goat and $75 to raise a pig, and she has $900 available for this project. Each goat produces $12 in profit and each pig $40 in profit. How many goats and how many pigs should she raise to maximize total profit? So again, start at the end. How many goats? Let's call that X. How many pigs? Let's call that Y. We're maximizing profit, so we know it's a maximize problem. Okay, so we're maximizing profit. You want to go back through and look at the numbers that are talking about profit. So don't just look for dollar signs. You might get tricked. The $25 is not talking about profit. The $12 is. So each goat produces $12 in profit, and pigs are $40 in profit. That means 12x plus 40y. That's my objective function, talking about maximizing profit. Now go back through again. Everywhere you see a goat is an X and a pig is a Y, but also look for inequality symbols. Raising goats and pigs wants to raise no more than 16 animals. No more than means less than or equal. So I know, okay, subject to, don't forget that. I know something is going to be less than or equal 16. Well, it's no more than 16 animals. So goats plus pigs has to be less than or equal 16. No more than 10 goats, so that's another less than or equal. Less than or equal 10, but this time it's only talking about goats. Goats was X, so I know X is less than or equal 10. She spends $25 to raise a goat and $75 to raise a pig, so we've got 25X and 75Y, and she has $900 available for this project. So here's where you have to kind of read between the lines again. $900 available for this project means she could spend $899, but she can't spend $901. So you're supposed to recognize that that means less than or equals. So the money available is less than or equal $900. So we would say 25x plus 75y is less than or equal 900. Now again, we need this extra little statement at the end just to produce, just to force us to not have negative pigs and goats. All right, that's our setup. Now we graph. Okay, you can kind of see where we're talking about, I think. Okay, dark region is right there. Now there's a lot of stuff going on, but I don't care about most of the stuff going on. I only care about the corner points. So these two are good, but this one, I don't care about this one. I want this one. And this one, I don't care about this one over here. So be very careful. Sometimes students will pick points that they don't care about. I don't care about this one. I don't care about this one. I don't care about this one over here. And I only care about these 5 points. So I'm going to draw another quick sketch. Look at what it's shaped like. Okay. So what do we have here? Start with the axis. And you have, it's like this and like this and like this. Maybe more like that. Okay, is that right? Something like that. It doesn't really matter. This, oh, that was vertical. Okay, so we want this last line to be vertical. No, that's terrible. That's fine, whatever. Okay. So the points were this one, 0, 0, and this one, and this one, and this one, and this one. Oops, let's go ahead and color in the feasible region. What's weird is I don't really care about any of those other points. I only care about the corner points. 0, 12, 10, 0. 6, 10, and 10, 6. Okay, those are my corner points. Take those corner points and plug them in to the objective function. 12x plus 40y. Well, this one's definitely going to be 0. The first one, 12 times 0 plus 40 times 0 is 0. 12 times 0 plus 40 times 12 is, what is that, 480. So times 6, and 40 times 10 is 472. And 12 times 10 plus 40 times 6 is 360. And 12 times 10 plus 40 times 0 is 120. So again, we're trying to maximize. We're trying to maximize profit. So the maximum Z number is 480 at 0, 12. So put it in context. We would say the max profit equals $480, raising 0 goats and 12 pigs. Excuse me. All of these problems are pretty much the same. So keep doing that. You got to read carefully to set it up and then graph. Number 3, certain animals in a rescue shelter must have at least 30 grams of protein and at least 20 grams of fat per feeding period. These nutrients come from food A, which costs 18 cents per unit and supplies 2 grams of protein and 4 grams of fat, and food B, which costs 12 cents per unit and has 6 grams of protein and 2 grams of fat. Food B is bought under a long-term contract requiring at least 2 units of B be used per serving. Another contract requires the amount of food B used be no more than 3 times the amount of food A. How much of each food must be bought to produce the minimum cost per serving? There's a lot going on here. You've got a lot of numbers. You've got food A, food B. You've got all kinds of stuff. So just be careful and start at the end. So what I'm going to do here, if I start at the end, how much of each food, that tells me that it's A and B. So let's say X is food A and Y is food B. I mean, technically, I guess you could use variables A and B if you want, but Desmos is going to make me put in X and Y, so let's just go ahead and do that. But also notice this time we are minimizing cost. So it's not a maximized problem this time, it's a minimized problem. Minimize Z equals. So the first thing I would do is I would go through and look for the numbers that are talking about cost. All right, cost. And so let's see. Notice you see cost 18 cents right there and cost 12 cents. All right, so notice they're talking about food A here and food B here. So you've got 18 cents for food A plus 12 cents for food B. Now, if you wanted to use 0.18 and change it to dollars, that's fine. Just make sure you're consistent and understand what you're talking about. If I use 18 and 12, I'm talking about cents. If you use 0.18 and 0.12, you're talking about hundredths of a dollar, which is the same thing essentially. Just know what you're talking about. All right, so that's our objective function. Now we want to subject to, abbreviated subject. Okay. So let's think about this. This one's kind of weird. We have at least 30. No, that's not less than or equal. At least 30 means 31, 32. That's greater than or equal. So there's going to be one of those constraints that's going to be greater than or equal 30. And notice it's talking about protein, so that's kind of important. And then we're going to have another one that says at least 20 of fat, so greater than or equal 20 for fat. Okay, these nutrients come from food A. All right, so check it out. When you've got food A, all of those numbers are going to have an X on it. So this is going to have an X, and this is going to have an X. Okay, but then when they start talking about food B is going to have a Y on it. That 6 is a Y, and that 2 is a Y. All right, so when you set this up, you have to pay really close attention. You have to be really, really careful, because that number 30 is talking about protein. So you only want to talk about other numbers that are talking about protein. So food A, it says 2 grams from protein. And then food B, where was it? It said 6 grams of protein. You go back and look at the ones that are talking about fat. The 20 was talking about fat. So make sure your other numbers that are talking about fat, that was this one and this one. You've got 4 for food A, and you've got 2 for food B. Alrighty, and then we keep going. It says food B, right here, food B is bought under a long-term contract requiring at least 2 units of B is used per serving. So at least means greater than or equal. And food B was just Y. So I've got this equation, Y is greater than or equal to, or inequality rather. Another contract requires the amount of B used is no more than 3 times the amount of food A. So that's kind of weird. So we've got food B, which was Y, is not more than. So think about what not more than is. Not more than means less than or equal. 3 times the amount of food A. So that was X. Food A was X. So all it says is Y is less than or equal, no more than 3X for food A. Okay? Now, don't forget your extra little statement here. You're going to need X is greater than or equal 0 to force, to keep me from having negatives. In this case, though, you don't need Y is greater than or equal 0. You don't need that because we already said Y was greater than or equal 2. So we don't need that extra step. It doesn't do anything for me. Okay? So there's our setup. We've got objective function and constraints. And let's go to Desmos and graph. Again, we don't graph the objective function. We only graph the constraints. There's the first one. All right, this one's kind of a mess. And this one's weird because we're minimizing this time, and so it's different. All right, kind of hard to see it. Let's change them all to the same color. All right, now it's much more obvious that the darkened region is like this. Okay, that's a weird, it's kind of a weird thing to do, but it's unbounded. Remember we talked about unbounded in the last lesson. This is unbounded. It would keep going on forever and ever. I could just keep going over and over and over and making this bigger and bigger and bigger, right? It is unbounded. But I can still do the same thing. I've got corner points here and here and looks like here. Those corner points. Everything else is just background noise and I don't really care about. All right, so let's draw a quick sketch. XY axis, this puts us in the first quadrant. Okay, let's take a peek. I've got kind of a steep one here and then a less steep one here. All right, so kind of a steep X. Yeah, kind of, oops. It looks something like that. Here, 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 here. Oh, and then a flat one. Okay. So we had a corner point here and, well, feasible region. Unbounded. And we had corner points here and here and here. So this one, 2, 6, 3, 4. So this was 2, 6. And this one was 3, 4. And this one, 9, 2. Okay, so, I've got a lot of information there. I didn't really do any tick marks. I don't really care about tick marks. All I really care about are those points. So be very careful when you're drawing this. And now let's plug into our objective function. Here's the objective function. Remember, that's 18 cents and 12 cents. So we've got 18 times 2 plus 12 times 6. So calculate that, you get 108. It's 108 cents. 3 and 4, 3, 4. 18 times 3 plus 12 times 4. It's 102. 102 cents. 9, 2. Plug that in. 18 times 9 plus 12 times 2. Again, I'm just looking at this objective function. That's going to be 186 cents. Okay. Talk about minimum cost per serving. Don't forget that word minimum. I don't want the maximum. I want the minimum. And the minimum this time is 102 cents. So it's 102 cents or $1.02 per serving. Okay. So the minimum cost per serving. You can either say 102 cents, or if it makes more sense to you, you can call it $1.02. With, where are we at here? This was my answer, right? 3 units of food A and 4 units of food B. One more. Happy Ice Cream Cone Company makes cake cones and sugar cones, both of which must be processed in the mixing department and the baking department. Manufacturing one batch of cake cones requires 1 hour in the mixing department and 2 hours in the baking department. And producing one batch of sugar cones requires 3 hours in the mixing department and 1 hour in the baking department. Each department is operated for at most 12 hours a day. Find the optimal strategy if Profits are $180 per batch of cake cones and $120 per batch of sugar cones. Okay, so we're talking about profit. And so think about it. Do we want to maximize or minimize profit? If we're talking about profit, we want to maximize. So this is a maximize problem. So, well, this one's kind of laid out weird, but in this one, we're talking about cake cones and sugar cones, but they're giving me the profit statement right here. $180 per batch of cake cones and $120 for sugar cones. So 180x plus 120y. Now I want to go back through and get my my constraints. So, a couple of things you can do is go back and every time it says cake cones, put an X, and sugar cones, put a Y. But also you're looking for the inequality symbol. So greater than, less than, something like that. So where are we at here? 1 hour in the mixing department, 2 hours in the baking department, producing 1, 3 hours in the mixing one. Okay. So where are we at? Yes. Took a while to find, but it says each department is operated for at most 12 hours per day. At most. At most 12. So at most 12 means like 11 or 10 or something like that. That's less than or equals. So we know less than or equals 12. And since it says each department, that's kind of a clue at how you're going to break this down. One of them's talking about mixing and one of them's talking about baking. There are two different departments, and both of them are at most 12, so you're going to have two different inequalities. So go through and look at the numbers that are talking about the mixing department. Mixing department. So cake cones requires 1 hour in the mixing department, and sugar cones requires 3 hours in the mixing department. So we're going to have 1x for the cake cones and 3y for the sugar cones. That was mixing. Now we're going to go back through and look at baking. So you have to be really organized. The reason that people are not very good at this is they're not organized. You have to really slow down and really think about what we're talking about. Now we're going to talk about the baking department. So we have cake cones were 2 hours in the baking and sugar cones for 1 hour in the baking. So that's 2 for the cake and 1 for the sugar. Going to look like that. All right, that's the hard part. Now don't forget about your extra statements. Extra statements help us avoid negative ice cream cones. All right, now the fun part. Go to Desmos and graph those inequalities. All right, so this one's straightforward. Maximize problems are usually a nice shape that we fill in. Okay, darkest region is in this quadrilateral, four-sided figure. Okay, occasionally you'll get a weird number like a decimal here. That's possible. That's fine. So here's what we've got, and we need to sketch that out. So I want a quick sketch. Don't skip that step. Don't be lazy. Here's my axis. I've got kind of a steep one and a not steep one. So I'm just going to kind of sketch this out. It looks something like that. Feasible region. And I've got corners. Here's one, here's one, here's one, and here's one. Obviously, this is the point 0, 0, 0, 4, and 60. And then that weird one, 4824. Okay. So here's our objective function. We plug those numbers in. So obviously this bottom one's going to be 0. 180 times 0 plus 120 times 0 equals 0. That's probably not going to be the maximum profit, as you might guess. 180 times 0 plus 120 times 4 is 480. 180 times 4.8 plus 120 times 2.4 is 1152. Okay, so we've got a new contender here, 1152. And then the last one here, 180 times 6 plus 120 times 0 was 1080. So this is kind of a weird question, all right? Obviously, our maximum here is 1152, all right? So obviously this one is the maximum, right? So how much profit should the company expect? I guess 1152, but, okay, but is it even possible to make 4.8 batches of cake cones? To make part of a batch. So it's kind of a confusing result with that decimal. So I guess, the short answer is 1152. That's the maximum number. I just have a question on whether or not you're even allowed to make a part of a batch. Maybe. I'm not so sure, though. So part C says, is it possible to make 3 batches of cake cones and 2 batches of sugar cones? About 4 cake and 6 sugar. Well, they're giving you ordered pairs, basically. So 3 batches of cake cones and 2 batches of sugar cones. Is that possible? Well, let's look at the graph. All right. So what if we had the point 3, 2? Oops. All right. See how that point right there, 3, 2, is inside the feasible region? That's inside the feasible region. That is right there, and that's possible. It's possible. It's not the maximum. I know the maximum has to be one of the corner points, but that is possible to do. We could do that. Now the other point, 4 and 6. So let's look at the point 4, 6. I don't even see that. Where is that? See that up here? That's way out here outside of the feasible region. Okay. 4, 6. Let's make that green or something. 4, 6 is up here. And that's not possible. Feasible means possible. So when it's outside of the feasible region, that's telling you that it is not possible.